The year is 2089. Professor Marcus Velasquez adjusts the quantum resonance detector for the third time this morning, his weathered hands trembling with anticipation. Deep beneath the Swiss Alps, in humanity's most sophisticated laboratory, he's conducting an experiment that could fundamentally change our understanding of reality itself. Today, for the first time in human history, he's attempting to measure the decay rate of the vacuum itself, the very fabric of space and time. The calculations spread across his holographic displays tell a disturbing story. According to quantum field theory, the state of empty space that surrounds us, that we call the vacuum, may not be truly empty at all. Worse still, it may not be stable. The equations suggest that our entire universe might exist in what physicists call a false vacuum, a temporary bubble of apparent stability floating precariously above an abyss of true nothingness. If the theory is correct, then everything we've ever known, every star, every planet, every thought and dream, exists only because the universe hasn't yet discovered its own death. We may be living in a cosmic house of cards, where a single quantum fluctuation could trigger the collapse of reality itself, spreading outward at the speed of light like a wave of pure annihilation. As Professor Velasquez initiates the measurement sequence, he contemplates the profound implications of what he's seeking. Is the universe already dead, existing only in the brief moment before its own demise? Are we witnessing the final act of a cosmic drama that began nearly 14 billion years ago, blissfully unaware that the curtain is already falling? To understand how we arrived at this terrifying possibility, we must journey back to the very beginning, to the moment when the universe first decided whether to live or die. The story begins not with a bang, but with a choice. A quantum decision made in the first infinitesimal fraction of a second after the Big Bang that may have sealed the fate of everything that would ever exist. In the beginning, there was inflation, a period of exponential expansion that stretched the universe from smaller than a proton to larger than a grapefruit in less time than it takes light to cross an atomic nucleus. During this cosmic birth spasm, the fundamental fields that govern reality were locked in a delicate dance, seeking their lowest energy states like water flowing downhill. But here lies the crucial question. Did these fields find their true lowest energy state? Or did they become trapped in a local minimum, a false valley that appears stable but conceals a deeper abyss below? The answer to this question determines not just the ultimate fate of the universe, but whether that fate has already been decided. The concept of vacuum decay emerged from the marriage of quantum mechanics and field theory in the latter half of the 20th century. Physicists realized that what we call empty space is actually a seething ocean of quantum fields, each vibrating at their minimum energy levels. These fields permeate every cubic centimeter of the universe, from the vast emptiness between galaxies to the spaces between atoms in our own bodies. The discovery that our universe might be fundamentally unstable came not from astronomy or cosmology, but from particle physics. In 1973, physicists Sidney Coleman and Frank DeLucia published a paper that would forever change how we think about the nature of reality. They demonstrated that if the Higgs field, the quantum field responsible for giving particles their mass, exists in a false vacuum state, then the entire universe could spontaneously decay into a lower energy configuration. This decay wouldn't announce itself with warning signs or gradual changes. Instead, it would begin at random points in space, creating bubbles of true vacuum that expand at the speed of light. Everything these bubbles touch would cease to exist in any recognizable form, as the fundamental constants of physics themselves would be rewritten. The mathematics of vacuum decay are as elegant as they are terrifying. The probability of decay at any given point in space and time is incredibly small, so small that the expected lifetime of our current vacuum state exceeds the current age of the universe by countless orders of magnitude. Yet the calculation also reveals that this decay is not just possible, but inevitable. It's not a question of if, but when. The discovery of the Higgs boson at the Large Hadron Collider in 2012 provided crucial data about the stability of our vacuum. The measured mass of the Higgs particle, approximately 125 billion electron volts, places our universe in a peculiar position. We exist in what physicists call a metastable state, balanced on a knife's edge between stability and decay. Further calculations, refined over the following decades, painted an increasingly complex picture. Our vacuum appears to be stable for now, but this stability depends critically on the precise values of fundamental constants that we're still measuring with ever greater precision. Small changes in these measurements could shift the universe from stable to unstable, or reveal that decay has already begun somewhere in the cosmic distance. The terrifying beauty of vacuum decay lies in its fundamental unpredictability. Unlike stellar death or galactic collision, which announce themselves billions of years in advance, vacuum decay could begin anywhere, at any time, without warning. The bubble of true vacuum could have nucleated in a distant galaxy yesterday, its deadly sphere of nothingness racing toward us at light speed, invisible until the moment it arrives to unmake everything we've ever known. This possibility forces us to confront one of the most profound questions in cosmology. What does it mean for the universe to be alive or dead? If vacuum decay has already begun in some remote corner of space, spreading its wave of annihilation across the cosmic landscape, is the universe already dying even though we can't yet see the symptoms? The concept becomes even more disturbing when we consider the role of consciousness and observation. In quantum mechanics, the act of measurement plays a fundamental role in determining reality. Some interpretations suggest that conscious observers are necessary to collapse quantum wave functions and make the universe real. If this is true, then what happens to regions of space where no conscious beings exist to observe them? Could vast regions of the universe already be decaying into nothingness, with only the presence of intelligent life maintaining local pockets of stability? This idea, while highly speculative, suggests that consciousness itself might be the universe's immune system, protecting reality from collapse through the simple act of observation and measurement. The search for signs of vacuum decay has become one of the most subtle and challenging pursuits in modern physics. Unlike other cosmic phenomena that reveal themselves through electromagnetic radiation or gravitational waves, vacuum decay leaves no trace until it arrives. The bubble wall of true vacuum moves at light speed, meaning that we can never see it coming. However, physicists have identified potential signatures that might reveal the presence of vacuum decay in distant regions of space. If a bubble of true vacuum were to nucleate within a star or galaxy, the sudden change in fundamental constants might create observable effects. Unusual patterns of light, unexpected particle emissions, or gravitational anomalies that could serve as early warning signs. Recent observations from advanced space telescopes have revealed puzzling phenomena that some researchers speculate might be related to vacuum instability. Certain gamma-ray bursts show energy signatures that don't match conventional models of stellar collapse or black hole formation. Some quasars exhibit spectral lines that appear shifted in ways that conventional redshift cannot explain. While these observations have alternative explanations rooted in conventional physics, they serve as reminders that the universe is far stranger and more complex than our theories suggest. Each unexplained phenomenon raises the question: are we seeing the universe as it truly is, or are we witnessing the afterglow of processes that have already fundamentally altered reality in regions beyond our cosmic horizon? The development of quantum field theory in curved spacetime has revealed additional layers of complexity to the vacuum decay problem. Einstein's general relativity tells us that matter and energy curve the fabric of spacetime itself. If vacuum decay occurs in regions of strong gravitational fields, near black holes or neutron stars, the interaction between quantum fields and curved spacetime might accelerate or inhibit the decay process in unexpected ways. Some calculations suggest that the intense gravitational fields near black holes could actually trigger vacuum decay by lowering the energy barrier that separates false vacuum from true vacuum. This possibility raises the disturbing prospect that every black hole in the universe represents a potential nucleation site for cosmic annihilation. Conversely, other theories propose that the expansion of the universe itself might provide a stabilizing influence, stretching the quantum fields and making vacuum decay less likely. The accelerating expansion driven by dark energy could be the universe's natural defense mechanism, preventing the formation of decay bubbles by continually diluting the quantum fluctuations that might trigger collapse. The role of dark energy in vacuum stability remains one of the most active areas of research in theoretical physics. Dark energy, which makes up roughly 70% of the universe and drives its accelerating expansion, might itself be evidence that we live in a false vacuum. Some models suggest that dark energy represents the slow decay of our current vacuum state, a gradual slide toward true vacuum that will accelerate over cosmic time scales. If this interpretation is correct, then the expansion of the universe isn't just carrying galaxies away from each other. It's the visible manifestation of reality itself slowly dissolving. The acceleration we observe might be the universe's death throes playing out over billions of years, too slow for us to notice within human lifetimes, but inexorable on cosmic scales. The implications of living in a false vacuum extend far beyond abstract physics. They challenge our fundamental assumptions about the permanence and reliability of natural law. If the constants of physics can change through vacuum decay, then everything we understand about chemistry, biology, and the possibility of life itself becomes contingent on the universe's continued failure to find its true ground state. This realization has profound implications for our understanding of time and causality. In a universe subject to vacuum decay, the future is not just uncertain, it may be fundamentally unknowable. No amount of scientific progress or technological advancement can protect us from a phenomenon that rewrites the laws of physics themselves. Yet there's something almost poetic about the possibility that we exist in a universe that hasn't yet discovered its own death. Like characters in a story who remain alive only as long as someone continues reading, we might persist only because the universe hasn't yet realized that it should collapse into nothingness. The search for alternative vacuum states has led physicists to explore increasingly exotic possibilities. String theory, which attempts to unify quantum mechanics and general relativity, suggests that our universe might be one of countless possible vacuum configurations, each representing a different set of physical laws and constants. In this multiverse of possible realities, vacuum decay doesn't represent the death of everything, but rather a transition from one universe to another. The bubble of true vacuum that destroys our reality might simultaneously create a new universe with different physical laws, different possibilities for matter and energy, and perhaps different forms of consciousness entirely. This perspective transforms vacuum decay from ultimate destruction into cosmic metamorphosis. Like a caterpillar dissolving into soup before emerging as a butterfly, our universe might need to unmake itself in order to become something greater. The wave of annihilation racing across space at light speed might be the universe's method of evolution, discarding old realities to make room for new ones. Recent advances in quantum computing have provided new tools for exploring the behavior of quantum fields and vacuum states. Quantum simulators can model the behavior of field systems that are impossible to study directly, revealing patterns and possibilities that might shed light on the stability of our own vacuum. These simulations have revealed that vacuum decay is far more complex than early theories suggested. The process involves intricate interactions between multiple quantum fields, each influencing the others in ways that can either promote or inhibit decay. The final outcome depends on a delicate balance of forces that we're only beginning to understand. Some simulations suggest that our universe might be naturally protected against vacuum decay by mechanisms we haven't yet discovered. The interaction between gravity, quantum fields, and the expansion of space might create feedback loops that stabilize false vacuum states, allowing them to persist indefinitely despite their apparent instability. Other models paint a darker picture, revealing pathways to vacuum decay that previous calculations missed. These studies suggest that certain high-energy processes, cosmic ray interactions, black hole evaporation, or even advanced particle physics experiments, might inadvertently trigger the collapse of local vacuum states. The possibility that human activity could trigger vacuum decay has led to intense debate within the physics community. Each new particle accelerator pushes deeper into unexplored energy regimes, potentially creating conditions that haven't existed since the first moments after the Big Bang. While the risk is considered extremely small, it represents a new category of existential threat. The possibility that our quest for knowledge might accidentally end everything. The Large Hadron Collider sparked particular concern when it began operations, as some calculations suggested that high-energy proton collisions might create microscopic black holes or exotic particles that could trigger vacuum decay. Extensive safety studies concluded that such risks are negligible, but they highlighted our profound ignorance about the true stability of reality. As we push toward even higher energies with future accelerators, these questions become increasingly urgent. Each new discovery in particle physics refines our understanding of vacuum stability, but also reveals new uncertainties and possibilities we hadn't previously considered. The anthropic principle offers a different perspective on vacuum stability. This controversial idea suggests that we observe a stable universe not because stability is common, but because unstable universes destroy any observers before they can make observations. In this view, our existence itself is evidence that we live in one of the rare cosmic regions where vacuum decay hasn't yet occurred. This reasoning implies that somewhere in the vast multiverse, countless universes have already succumbed to vacuum decay, their stories ending before intelligent life could emerge to tell them. We exist in the narrow window between cosmic birth and death, conscious observers in a universe that hasn't yet realized its own mortality. The measurement problem in quantum mechanics adds another layer of complexity to vacuum decay scenarios. If consciousness plays a role in collapsing quantum wave functions, then the presence of intelligent observers might actually influence the probability of vacuum decay. Our very existence as conscious beings might be stabilizing the universe around us, preventing reality from dissolving into quantum uncertainty. This idea suggests a profound connection between mind and matter, consciousness and cosmos. We might not be passive observers of the universe, but active participants in its continued existence. Our thoughts, observations, and measurements could be the threads that hold reality together, preventing it from unraveling into the nothingness that quantum mechanics suggests is always just one fluctuation away. The role of information in quantum mechanics has led some physicists to propose that vacuum decay might be fundamentally limited by information-theoretic constraints. The holographic principle, derived from black hole physics, suggests that all the information in a volume of space can be encoded on its boundary. If true, this might prevent vacuum decay from completely destroying information, ensuring that some record of our universe persists even after physical reality collapses. These ideas blur the boundary between physics and philosophy, science and spirituality. They suggest that the universe might be more than just matter and energy obeying mathematical laws. It might be a vast information processing system, a cosmic computer calculating its own existence moment by moment. Professor Velasquez, still monitoring his quantum resonance detector in the depths of the Swiss Alps, represents humanity's ongoing effort to understand these profound questions. His measurements probe the very foundations of reality, seeking to determine whether our universe is truly stable or merely hasn't yet discovered its own instability. The data flowing across his screens tells a complex story. The quantum fluctuations he measures are consistent with a false vacuum, but they also reveal structures and patterns that don't match theoretical predictions. The universe appears to be more stable than pure quantum field theory suggests, as if additional forces or mechanisms are at work to maintain reality's integrity. As he analyzes the results, Professor Velasquez realizes that he may be witnessing something unprecedented in the history of science. Direct evidence of the universe's immune system, the quantum mechanisms that protect reality from collapse. The vacuum isn't passive or empty, but actively maintains its own stability through processes we're only beginning to glimpse. This discovery transforms our understanding of cosmic evolution from a story of inevitable decay to one of dynamic stability. The universe isn't just dying slowly, it's actively fighting for its own survival, using quantum mechanisms to repair and reinforce the fabric of spacetime itself. The implications ripple through every field of science. If the vacuum is self-stabilizing, then the universe might be far more resilient than we imagined. The constants of physics might not be fixed parameters, but dynamic quantities that adjust themselves to maintain stability. Reality itself might be evolving, becoming more stable and more capable of supporting complex structures like galaxies, stars, planets, and life. This perspective suggests that consciousness and intelligence aren't accidents in an indifferent universe, but inevitable outcomes of cosmic evolution. The universe might be developing the capacity for self-awareness not as a side effect of physical processes, but as a fundamental feature of its own stability. Mind might not emerge from matter, matter might emerge from mind. The search for extraterrestrial intelligence takes on new significance in this context. If conscious observation stabilizes reality, then the distribution of intelligence throughout the universe might determine the overall stability of spacetime itself. Finding other conscious civilizations wouldn't just answer questions about our cosmic loneliness. It would reveal the universe's immune system in action. Recent observations from advanced telescopes hint at this possibility. Certain regions of space show unexpectedly low rates of high-energy phenomena that might be associated with vacuum instability. These cosmic quiet zones might be maintained by the presence of advanced civilizations that have learned to stabilize their local regions of spacetime. The Fermi paradox, the apparent absence of detectable alien civilizations, might reflect not the rarity of intelligence, but its tendency to operate in ways that prevent cosmic instability. Advanced civilizations might naturally develop technologies and behaviors that maintain vacuum stability, making them invisible to our searches, but essential to the universe's continued existence. This hidden community of cosmic gardeners might already be at work throughout the universe, tending to the quantum fields that maintain reality's stability. Our own technological development might be preparing us to join this cosmic maintenance crew, learning to take responsibility for the stability of our local region of spacetime. The future of humanity, in this view, isn't just about expanding into space or developing new technologies. It's about learning to protect reality itself. We might be evolving from passive observers of the universe to active participants in its continued stability. Our destiny might be to become the universe's neurons, conscious nodes in a cosmic network that thinks itself into continued existence. As Professor Velasquez completes his measurements and begins the long process of analysis and verification, he contemplates the profound responsibility his results might reveal. If consciousness truly plays a role in maintaining cosmic stability, then every human mind becomes a guardian of reality, every thought a contribution to the universe's continued existence. The question of whether the universe is already dead transforms into something more hopeful. The recognition that through our very existence as conscious, observing beings, we participate in keeping the cosmos alive. We are not passive witnesses to cosmic evolution, but active agents in the universe's ongoing struggle to maintain its own existence. In this vision, the universe hasn't discovered its own death because it has discovered something more powerful, the ability to sustain itself through consciousness, observation, and understanding. Each moment of awareness, each act of measurement, each scientific discovery strengthens the quantum threads that hold reality together. The cosmos continues its ancient dance between existence and nothingness, stability and decay, but it no longer dances alone. Consciousness has emerged as its partner, and together they weave the ongoing story of a universe that chooses, moment by moment, to continue existing. In our questions about cosmic death, we find the seeds of cosmic life. In our fear of universal decay, we discover our role as universal gardeners, tending the quantum fields that make reality possible, and ensuring that the universe's story continues to unfold across the vast theater of space and time.